Hi everyone, my name is Akash Maharaj and I'm really excited to talk to you today about a project that we've been working on in Adobe Target, which allows us to use custom or unknown machine learning models on our edge servers around the world to make real-time decisions about what content to show users. This is work that I've done with my amazing co-presenters, Georgiana Copil and Iulian Radu, who you'll hear from in a few minutes, along with a few other really talented team members here at Adobe. So first, an outline of today's talk. I'll give a short introduction to the type of machine learning that we do in Adobe Target and try to set some business context for why we're interested in the problem of scoring unknown or custom machine learning models in real time. I'll then hand it over to Georgiana and Iulian, who will take you through the various challenges we faced in creating this product. And they'll discuss some of the trade-offs we considered and the pragmatic approaches that we eventually landed on for solving these problems. So first, an introduction to Adobe Target. Adobe Target is a product within Adobe's Experience Cloud, which sits alongside the Creative Cloud and Document Cloud here at Adobe. The Adobe Experience Cloud is a series of business-to-business solutions for digital marketing and e-commerce. The suite of products in the Experience Cloud weaves together everything from analytics to content optimization at scale. Our product, Adobe Target, is the experience decisioning engine of the Experience Cloud. We essentially make real-time decisions of what to show our users' customers on websites for the purposes of experimentation and optimization. We have over 1,000 customers worldwide, including many major brands in e-commerce and retail, digital publishing, financial services, and travel and hospitality. So when you visit the web pages of our customers, Adobe Target makes the decision about what content you should see on those pages. So for example, everything from the colors of buttons to what banner images are shown to you on a home page, to what trays of recommendations should contain on a product page. A call is fired from those web pages to our personalization edge servers around the world, and then Adobe Target decides what experience someone should see. So the primary customer persona for Adobe Target is a marketer at one of these large corporations around the world. And they choose the experience decisioning logic from one of several different types, which are the squares in this diagram. These experience decisioning types sit in various conceptual logics, three of which are depicted here: experimentation, personalization, and recommendations. And each grouping has different levels of sophistication. For example, for experimentation, marketers can choose between simple A/B tests or multivariate tests, or even in a more sophisticated manner, continuous allocation to a winner, i.e. multi-arm bandit style allocation. For personalization, or when the number of experiences to choose is fairly low, they can choose to do rules-based targeting, or they can choose between a couple of different automatic or machine learning driven selection strategies. Finally, when we're dealing with large product catalogs and where the number of experiences to show can be in the millions or billions, marketers would like to show product recommendations. And we have a suite of recommendation algorithms that they can choose between, with everything from collaborative filtering down to personalized recommendations. So as you can see from this list of features, the ones which require more advanced machine learning are the auto-allocate, auto-target, and automated personalization products, as well as, of course, the recommendations algorithms. So in today's talk, we'll be focusing on the auto-target product, which selects the best holistic experience to show each visitor on each visit to our customers' websites. So what is the auto-target product? Our out-of-the-box algorithm is essentially an ensemble method of machine learning, which combines non-contextual Thompson sampling with an epsilon greedy random forest. The random forest basically uses customers' profile values, like the number of previous times we've seen this end user, the profile segments that that end user belongs to, as well as contextual data like the time of day or the URLs that they have visited in this current session, and other real-time data to choose the best experience. So at its heart, in machine learning vocabulary, this is a binary classification problem. We're basically deciding whether or not a user will convert on a given experience given their user profile and their context. And we will then choose which experience to show them based on the experience that has the highest probability of conversion. So our random forest basically today has an automated feature selection pipeline, which chooses from these hundreds of features that we have available to us. But of course, creating a single model and using a single automatic feature selection strategy across all of our customers, it may not always lead to the best performance. It's a sort of one-size-fits-all approach. And of course, as our customers become more sophisticated and as data science becomes more commoditized, their data scientists are hungry to create models of their own and apply their domain expertise and their knowledge about their customers to their personalization strategies. And so this is the problem that we set out to solve. We wanted to allow our customers to bring their own machine learning models to replace the random forest at the heart of Adobe Target's algorithms. Of course, this brings significant problems. Everything from what contracts should models support to what types of models and frameworks should we support, like TensorFlow or Spark, what serialization format should we use? And actually, most importantly, how could we execute our customers' untrusted code on our edge servers around the world and guarantee both stability and performance? We need to maintain P99s of serving of under 10 milliseconds. So these are the types of problems that we have to think through. And now I'll hand it over to Georgiana and Iulian, who'll describe these problems in more depth, and then, of course, the solutions that we came up with.
To be able to run inference on custom models in the edge, we had to do two things. To support the data scientists in creating their models, this including also providing all the necessary data, and running the model in the edge. For the first part, we are pushing the data into Adobe Experience platform for it to be available for training. The data scientist can use the data science workspace from platform to access this data and to train and publish their models. For the second part, we can download the model from the data science workspace, store it into our model repository together with the rest of our models, of the target models, and use it from the personalization edge at runtime for inference. Sometimes this is easier said than done. The challenge is that we have multiple languages and frameworks available in the data science workspace, which is very good for data scientists because they have so many options. It's a bit challenging for us because on the personalization edge, we are solely running on Java. We had the option of running each model in an isolated environment, but we were a bit concerned of the extra hop that each request needs to do and the extra management of infrastructure. So we decided to stick with Java and to use the same Java runtime for inference without adding model inference as a separate service. This way, we decouple the complexity of the multitude of frameworks that are being used at training time from what we need to have at inference time. We made this decision also having in mind that we should keep our current response time, which is P99.5 less than 5 milliseconds. And this decision actually gave birth to our next challenge. We need a way to encode models, transport them, and execute them. And that encoding needs to be interpretable in the same way, regardless of the environment or language that we're running. In other words, we need a format for representing our models, if possible, a widely accepted standard. We looked into the options for representing our models, and we found several, such as ONNX, which is pretty used, but ONNX runtime at its core is a C implementation. So in the edge, in Java, we will need to use GNI implementation in order to do the inference. PMML had very limited Java support. MLeap had little traction at that time, and we were interested to use something on the long term. So at the end, the decision was to use ONNX. It has converters available from multiple machine learning frameworks, and it seemed the most mature out of the ones that we have checked. So going back to our custom model view with this decision, we now have ONNX. which is good. But as there always is a but, we needed to ensure that we have the same feature processing both in the data science workspace and in the personalization edge. This is to ensure that we can perform inference in the edge. That's one thing that's very important. And the other thing, that the result is not complete nonsense. One challenge we ran into was that in ONNX, we are still missing some operators, for instance, string imputers. Additionally, just for very few frameworks, we have processing pipelines packed together with the model and encoded in ONNX. We actually found just sklearn doing this. So our solution was to produce a library through which the user can tell us exactly what transformations are needed on the data. Our target preprocessing library produces a metadata of all the operations performed in what essentially is a DSL. This metadata is then interpreted in the edge to generate the same values you would have generated in the data science workspace. And actually, the same values you generate in the data science workspace through the use of our library. Coming back to our big picture, we have managed to get the model in the edge and understand what we should do with it. Now, moving forward, the model should expect the same inputs and give the same outputs both in the data science workspace and in the edge. This is pretty tricky considering that we have multiple frameworks in which the models are trained and multiple tools that convert the model to ONNX. For the case of inputs, we noticed that the ONNX converters are quite opinionated. For instance, sklearn to ONNX validates that there are no dots in the name, also no other types of separators, and replaces them with underscore. TensorFlow to ONNX, so TF to ONNX, appends a colon and a 0 to the input names. So if we take an example, test.test from sklearn to ONNX would become test underscore test. Test.test from TensorFlow to ONNX would become test.test colon 0. Therefore, we added in our library some steps of validating the input names and cleaning the input names from the ONNX graph to be in accordance to what we know has been sent to the model. Similarly, the input shapes need to be something that we can pass in the edge as well, and as well the types. So we also added validation that checks the input types and shapes to be something that we can use in the edge in ONNX runtime. We decided to set in place as much validation as possible in this library in order to make sure that the data scientist receives early feedback on whether we can use or not the model and what are the problems, and not wait until we try to download or to run the model in the edge, because the feedback loop would be unnecessarily long. For the outputs, the pain point is that in some frameworks, the user has a lot of freedom on how the output will look like, and that different converters convert using different data types depending on the model. For instance, sklearn to ONNX would give us as output an ONNX sequence, while TensorFlow to ONNX would give us as output arrays. So to make sure that we can properly interpret the output, but also that the user receives early feedback on whether the model created is acceptable or not, we defined the supported output types and added output validators to our library.
We will now cover the security and stability aspects of our implementation. Adobe Target Personalization Edge serves a large number of customers. Some of them will use the custom model feature described in this presentation. Our duty is to make sure that misuse from a customer does not affect other customers in any way. Let's see what are the possible problems we can encounter. We'll start with the model generation side. As you've seen from the overall architecture, the data scientist is responsible for converting the model to ONNX and packaging it together with the metadata. Adobe Target provides a library for simplifying the process, but it's up to the customer to use it, and they may choose not to do so. This means it is possible to receive a payload that is not conforming to our packaging expectations. In order not to waste CPU cycles on the edge servers, we handle all validation in a separate model download job. The job periodically fetches Any new models uploaded by our customers to their data science workspace model repository and runs a series of validation steps, starting with the simple ones, like checking if the expected files are present, or if the package size is under some agreed upon limit. It will then deserialize the model, validate assumption regarding the model's inputs and outputs, and run an inference with random input data in order to check the model's inference time is within the expected limits. The attack vectors we've considered are exploits of the various libraries being used, like the Java unzip library, the ONNX runtime, or the Jackson.json library. For the Java unzip functionality and Jackson library, we consider the risk of exploitability being low, since they are used at a massive scale. The ONNX runtime risk of exploitability is higher since the library is in its infancy, but there are currently no known vulnerabilities and the community is pretty active, so we expect them to be fixed as soon as they are identified. Another possible attack vector that could be used is to exploit common library misuse defects, like directory traversal attacks and denial of service attacks when a small zip archive can be extracted into a very large object, in the case of the unzip library, or arbitrary object deserialization attacks when talking about JSON deserialization. We have tried to avoid these problems during the implementation and follow best practices, but also preventing them from propagating outside the validation job by running the validation inside a resource-limited container with some limited sandboxing. The most likely attack vector on the inference side is a denial of service attack from noisy neighbors that could be keeping the CPU or processing threads busy for long periods of time. The native ONNX runtime library provides support for stopping the inference early, and luckily, the Java bindings for the latest version include that capability as well. So we can now stop inference for long-running models without forcibly stopping the inference and leaking unmanaged memory. Let us now turn our attention on the model update process. The challenge is to use the model for inference on the edge as soon as possible after the data scientist published the model into the data science workspace model repository. Our current implementation uses a polling mechanism for checking for newly updated models every 2 hours. For the future, we are exploring switching to a notification protocol in order to reduce the latency to a few minutes. Now, let's talk about one minor inconvenience. After using platform-independent programming languages for a long time, one may forget about the headaches generated by supporting multiple platforms in a native library. Here are the different platforms we need to support at the moment. Individual engineers use MacBooks for development, our download job runs in a CentOS environment, and our edge inference is done on containers using Alpine Linux. The Java bindings for the ONNX runtime makes use of JNI for delegating the work to the native implementation. Prior to version 1.3.0, the ONNX runtime didn't support cross-platform jar packaging. So we had to build multiple jar files, one for each platform, and make sure they are made available on the class path when running our application. However, since version 1.3.0, the ONNX runtime supports packaging libraries for different operating systems and architectures in the same jar file. This means that in theory, we can now use a single jar, regardless of platform. The new packaging systems seems to be running well on macOS and CentOS, but it's still having some troubles on Alpine Linux. Now, summing things up, we are really excited by the speed of development of the ONNX runtime. All the missing functionality we felt was needed was added to it before we could react and make a contribution ourselves. This rapid pace of development gives us confidence that ONNX will be a long-lived representation format and will see continuous improvement over the next few years at least. We are also excited to put Adobe Target custom model feature in the hands of data scientists all over the world and looking forward on receiving feedback on how well it works in practice. The future will bring emphasis on non-functional aspects. We have to evaluate if a switch to a single tenant approach is needed for edge inference. And we also need to help data scientists evaluate the model quality before deploying it on production. Last, we will want to observe if the ONNX runtime default accelerator offers satisfactory performance for the models used by our customers and explore using different accelerators if needed. Thank you for listening. We hope you have found this presentation useful and it will help you when designing something similar to it. Many thanks to the rest of the team and of course to all the ONNX runtime contributors which made this project possible in the first place.